I'm very pleased to be here to present my work on modeling the urban boundary layer under the influence of a sea breeze and using high-resolution large-eddy simulations. So, brief outline of this presentation is I give a short introduction to sea breezes in urban areas, briefly discuss the methods and the case study we are doing, and show some qualitative results, and then discuss about the future work we have ahead. So sea breeze is a thermally driven mesoscale circulation, shallow circulation within the boundary layer. Its horizontal extent is from 2,000 to 2,000 kilometers in size, usually around 20 to 100 kilometers. It arises from the differential heating of sea and land surfaces, because the surfaces tend to have higher heat capacity, so the solar radiation heats the land surfaces faster. And of course, because this arises from surface forcing, it is of great interest at how urban areas influence the sea breeze. It doesn't change. Yep, thanks. So our research aims in our study is to quantify the urban influence on sea breeze circulation strength, inland travel velocity, and inland penetration distance. And we also focus on resolving and understanding the urban and also non-urban thermal internal boundary layers forming in the sea breeze gravity current and its turbulent processes. So the gravity current is this coastward flow of colder air from the sea. We also want to quantify the effect of turbulent mixing across the sea breeze front. So it has been suggested that this turbulent mixing causes turbulent frontalysis of the front. Next. We use large-eddy simulations, LES. We want to avoid the gray zone altogether by resolving the at least most of the turbulence, let's say 95%. That way we can avoid relying on parameterization and how turbulence is presented in those parameterizations. We use the PAL model system, open source LES model, with some own customizations. We run 2+1 simulations of a single case study, varying the surface distribution between the simulations. The LES model is offline nested into a mesoscale model harmony around run at 2.5 kilometer horizontal resolution, and the boundary is updating every 15 minutes. We impose synthetic turbulence generator on the boundary conditions to have the turbulent part of the boundary condition. Next. Our case study is a springtime case study. We are in Northern Europe, in Helsinki, with an urban population of around 1.3 million. So not as large city as New York, definitely. It's a coastal city, the northern coast of Gulf of Finland and the Baltic Sea. Our case study is in April, and we have quite favorable geostrophic winds, in this case for sea breeze circulation to form, so 8 to 10 meter moderate geostrophic wind from north to northwest. One thing about why this particular location is also very nice for studying sea breeze is that we have a vast measurement network. So we have 2 urban eddy coverage sites here in Helsinki, and we also have Doppler LiDAR, a few ceilometers, and a C-band drop polarization radar, and a lot of official and unofficial weather stations. Our simulation domain is 74 kilometers by 46 kilometers by 3.6 kilometers, and we use 24 meter horizontal resolution and 8 meter vertical resolution, but the vertical bridge is stretched over 1.2 kilometer up to 24. We run the simulations for 17 hours from 3 a.m. in the morning or in the night. We have three different surface descriptions, or two, now currently only two, but in the future three. The first one is kind of non-urban case, so we have no built fraction. Fluxes are online model using Baum's lens surface model, which is based on 8 decile of IFS. Then we have a natural plus urban EC case, where we still run the lens surface model, but together with that, we use spatial mapping of field fraction to input urban fluxes based on eddy covariance measurements. So we input sensible heat flux, latent heat flux, and friction velocity. Then in the future, we also want to model the urban fluxes online using a coupled single layer urban canopy model implementation currently under implementation for Palm. Not ready yet, future work, but hopefully we can go through it in the next couple of months. Our domain vertical composition looks something like this. So at the top we have the offline nesting, the harmony around. Then we dampen gravity waves using Rayleigh damping layer. We have the vertical grid extraction layer, and below 1.22 meters we have the 8-meter vertical resolution. We have three different types of surfaces: sea surfaces, land surfaces, and mixed urban land surfaces. The major limitation here is that we have only prognostic equation for sea surface skin temperature, but not for the sea surface temperature itself. So that is constant during the model run. But the actual skin temperature, of course, changes and is modeled using the land surface model. So a qualitative look on the results. I'm a bit reluctant to show any numbers here because there are still some issues to iron out. But slide here is an example of 2-meter air temperature at afternoon. We can clearly see that we are able to produce the sea breeze in both cases. And what's interesting here from urban perspective, that we see a quite large accumulation of urban heat behind the sea breeze front, where the wind speeds are quite low. Also, another interesting thing compared to the natural case is that we kind of see like a hybrid between sea breeze and this kind of country breeze. So there is an inward flow also from the land area towards the city, where the heat flux is sensible heat flux is higher. Next. Then looking at the vertical structure, and especially comparing to Doppler LiDAR observation from an urban site 6 kilometers inland, we can see that when we look at the urban case, the boundary layer height and growth is approximately correct. So we get the boundary layer total height during the afternoon is around the same we see with the LiDAR. However, the sea breeze gravity current, which is this red flow towards the coast, is much stronger and shallower than observed. But the one thing to note also from here is that when taking the urban fluxes into account, the timing of when the sea breeze front arrives at this particular site is pretty much the same as we see in observation. But if we don't input the urban fluxes, then the sea breeze front is delayed up to 2 hours from the observed. So we can see an urban effect on the inland travel velocity of the sea breeze front. So what's next? As I said, we want to quantify the urban influence, and we are very well aware that just using measurements as an input is not resolving the feedbacks itself. So we definitely want to run these simulations with the modeled with the single layer urban canopy model implementation and to see if there are any differences between the when just inputting the measured fluxes. We have to do a few technical adjustments still. As you can see, we are not close with vertical structure yet. I have to make some sensitivity tests with the sea surface temperature, for example, to see if the gravity current, like the depth of the gravity current, could be resolved by changing the sea surface temperature dynamically over the simulation. After this, we are going to do extensive validation against the measurement network because as great LES is, you have to always do a lot of validation because there are so many ways to set up the simulation wrong, incorrectly. And after this, we are digging deeper into the data. We want to see the implications for urban eddy coverage measurements, what uncertainties these thermal internal boundary layers can cause to these measurements on air quality, NVP, and climate modeling. Thank you.
Thank you very much, Sasu, for taking us to the north of Europe, to the northern hemisphere, from the southern hemisphere. Right. Who would like to ask a question or two?
I have saw results in comparison to the LiDAR. Shows that the peak of the sea winds maybe is quite shallow compared to LiDAR's measurements. Do you think that it could be some things like the surface that is difference or too small to induce the model, so it causes this problem?
I haven't really figured it out yet. My kind of initial guess is that because the volume flow of the gravity current seems to be around the right magnitude, the problem is that the layer is too shallow, which makes the gravity current wind speeds too fast. So my initial guess at this point is that the sea surface temperatures might be a bit cold compared to the what was the reality in this case. But I have to do some sensitivity test and check if that resolves the issue of the gravity current.
Thank you. Any other question?
Hi, thanks. So
It's on.
It's on.
Okay, thanks. That's a presentation question for you, but also for David. So two different approaches in both coastal cities equipped very well equipped in terms of LiDAR and our measurements. So what do you think about so how important is the validation that you're getting, that you're performing, and what do you think about cities where such infrastructure is not available? We shouldn't do any simulation at all.
Thanks for the question. It's a very important and difficult question to answer, but I would say in my case it's vital that we have, for example, Doppler LiDAR to validate this, because even the surface temperature, 2 meter surface temperature could look like compare well against the weather stations, but we still would miss the whole vertical structure. So with LiDAR, we at least see if we are wrong, and in this case, we are still a bit wrong with the vertical structure. So it's kind of this kind of iterative process to get the simulation set up just correctly, so it can compare well against the measurements. I would say if there are no these kind of vertical profiling measurements available, it's probably not recommended to do LES of sea breeze, for example, where this vertical structure really matters. But there are, of course, many other questions to study with LES where this questions don't, where the vertical structure is not as important.
Thank you. And
Beyond identical question.
oh, okay, that makes life easy, but nobody else. Otherwise, there's always beer.
That's my last question. So are you sure you still want another beer?
Okay, that was the last question of this session. Excellent, thank you.
We can discuss that later.
Yeah. Okay, so great. Just let me add a few things here. So this session now is followed by a tea break, half an hour, and